Okay, welcome back. Hopefully you thought this joke was funny. And now that you know what a complex number is and an imaginary number, let's move over to talking about the arithmetic of complex numbers. So when we're talking about the arithmetic of complex numbers, what we want to know is how do we do the basic operations of addition, subtraction, multiplication, and division with these numbers. So first of all, let's kind of set up our notation and explain how we're doing things. So first of all, we're going to write a complex number as usually you write Z to denote a complex number, and you want to remember that this means A plus BI, where A and B are real numbers. We can talk about the real part of a complex number, and sometimes we write it as RE of Z, and that would be the A part, that's the real part. And then the imaginary part is the part that goes in front of the B, that is connected with the I. So we would denote it as I am, Z for imaginary, and then that would be B. So as examples, if I had Z is equal to 3 minus 2I, that would imply that the real part of Z is 3, and the imaginary part of Z, let's clean that up there. The imaginary part of Z is negative 2. Okay, because we're always thinking of complex numbers as A plus something. So we want to think of this as 3 plus negative 2. Now, of the operations, addition, subtraction, multiplication, and division, addition and subtraction are the easiest to describe. So how do you add two complex numbers? Well, here I have two complex numbers. You add them by adding the two real parts, and that gives you the new real part. And then you add the corresponding imaginary part. So you have B plus D times I. So that's just a sum of two complex numbers. Subtraction is done in the same way. You subtract the real parts of both of them, and then you subtract the imaginary parts of both of them, and that becomes your coefficient of I. Multiplication is also kind of straightforward. You want to, if you remember the rules of FOIL, you just have to expand these out. So first of all, just do regular multiplication. So you would have A times C plus AD times I, and then plus BC times I, and then you have B plus D times I squared. And then what you want to do is you want to simplify it. But as you're simplifying it, the first thing that you want to remember is that I squared is equal to negative 1. So I'll rewrite this. So I have AC plus ADI plus BCI minus BD, because I can replace I squared with negative I. And then I group together the real part, AC minus BD, and then I group together the imaginary part. And there you go. That's the formula for multiplying two complex numbers. And I think I have an example right down here, so let's expand it out. So you could just jump right to the formula, but how about I just write everything out in the gory details. So we have 2 times 4, which is 8, plus 2 times 6i, which gives me 12i. And then I have 3i times 4, which gives me another 12i. And then I have an 18 times an I squared. So this gives me 8, then I have 24i, and then I have a minus 18. And then it simplifies to minus 10 plus 24i. So that gives me the answer to multiplying these two complex numbers together. Now division is a little bit more complicated, and we just introduce some more terminology in order to do division. So for division we need two operations, and both of these operations will show up in the rest of this course. So we have the notion of a conjugate. So the conjugate of a complex number is just the number, we write Z bar to denote the conjugate, and it's the number that you get by just changing the sign of the number in front of the imaginary number. So what was A plus BI becomes A minus BI. And then the modulus, and we write it kind of as absolute value of Z, is take A squared plus B squared, and then you take the square root of that, and that's called the modulus. So as examples, if z is equal to 2 plus 3i, the conjugate is the complex number 2 minus 3i, and then the modulus is 2 squared plus 3 squared square root. And so this is 4 plus 9, so we get the square root of 13. So I have the conjugate and the modulus. And the reason we introduce them is because division is normally defined in terms of the conjugate and the modulus. So if you have two complex numbers, a plus bi and c plus di, the z1 divided by z2 is defined to be z1 times the conjugate of z2 divided by z2 times the conjugate of z2. And you can actually rewrite this as z1 times the conjugate of z2. And then downstairs, you can show that this is equivalent to the modulus of z2 squared. Now, if you don't like this so much, it gets a little confusing. Here is the formula in terms of the a, b, c's, and d's. So if you have a plus bi over c plus di, when you divide it, what you're getting is a plus bi times c minus di, that's the numerator. And then downstairs, you're going to get c squared plus d squared. Because c squared plus d squared square root is the modulus, but we're squaring it, so we're getting rid of the square root sign. And if you apply the formula just to a plus bi and you're taking the reciprocal, if you want to find 1 over z, so you just apply the formula, and as an answer here you would have a minus bi over a squared plus b squared. And let's do one example before we take a break in today's lecture. And maybe you might want to pause it right here, see if you can compute it, and then come back and see if you're going to get this answer. So using the formula that's up here, I'm going to calculate it. So I get 1 plus I, 2 minus 3i upstairs, and then I have 2 squared plus 3 squared downstairs. So I'll multiply out the top. So I get 2 minus 3i plus 2i, and then I get negative 3i squared, which gives me plus 3. And then downstairs gives me a 13. And so upstairs I get 5 minus I over 13. And you may want to write it in the form of a complex number where we have the real part and then we have the imaginary part. There we go. And that would be our answer to the problem. Okay, hopefully you paused and you took a break and tried the answer, and that's the answer you got. If so, good job. Give yourself a happy face. So I'm going to give myself a happy face because that's the answer. And we'll pause and come back to talk about some of the geometric meaning of what we just did.